Hello, we are going to see the solutions of photoelectric effects from SC Verma, SCV. That is question number first. They have given visual light has wavelength in the range of 400 nanometer to 780 nanometer. Means if you see the lambda 1 is given to be 400 nanometer and lambda 2 is given to be 780 nanometer. Okay. Calculate the range of energy of the photon of the visible light. We have to calculate the range of energy of photon. Here you see, if you here the wavelength is less, so energy will be maximum, and here the wavelength is more, so energy will be minimum. So that will be the range that we have to find here. So energy is written to be hc by lambda. So here we will write that is the max, and here you will write minimum, that is the hc by lambda 2. So if you calculate anyone, so emax, it will be 6.64 10 to power minus 34, and that is c speed of light 3 into 10 to power 8, and divided by lambda 1. Lambda 1 is given to be 400 nanometer, that is 10 to power minus 9. So how you have to calculate this? You see how you have to take the approximation. You see, if I cancel this will be minus 7, 10 to power minus 7, and it will go in numerator. So this is plus 7, so 15, and here the 34. So you will find 19, that is the 10 to power minus 19. So here will be 6.64, that is 3 divided by 4, and that is the 10 to power minus 19 joules. Okay, so now you have to do what? You will see that here the energy you will find, this is almost 20, and divided by 4 into 10 to power minus 19. So we'll find 5 into 10 to power minus 19 joules. So that will be the maximum energy in this range. Now we'll calculate the E minimum, that is the minimum energy we have to calculate. So you will write 6.64 10 to power minus 34. Same thing we have to do here, 3 into 10 to power 8, and that divided by the 780 into 10 to power minus 9. So again you see, you solve this if you solve, so and you take mm, this, so you will be 9, this 9 17, that will be 17 also. This will be how much? You see 9 and 8 here, that will be added. So 17 and 17 to 34, so that will be, you see, you will find 6.64, and that is 10 to power minus, here 3 is remaining also, 3 and 10 to power minus 17, and that is divided by 780. So you see that will be almost 20, and so you find 20 and divided by 780, that is 10 to power minus 17. So almost you will find this 0 cancelled, so here double 0. If you calculate this, so you will find almost 2 0 point, if you calculate this is 2 ones are 1, this is 3, that is 9. So 1 by 39 10 to power minus 17. If you solve this, so at least you have to write 100, and that will be 10 to power minus 19, and that is 39. So 39, that is almost near to the 40. Means you will find 2.5 almost, and this is less than 40. So that's it. There will be some digit like 4 5, there will be something. Okay, so we'll take 6, that is minus 19 and joules. So you have to see how we have to approximate these things. Now we are coming to the question number 2. What the question number second says, calculate the momentum of photon of light of wavelength 400 nanometer. So you know momentum p is given by h by lambda. So that h is nothing but 6 point, that Planck's constant 6.64 10 to power minus 6.64 10 to power minus 34 and divided by lambda. So lambda value is given to be 500 nanometer, that is 10 to power minus 9. So you see that is 6.64, that 10 to power minus 34, and it will go numerator, that is 9, and that is 500. So you see, you 100 you take here, so it will be minus 2 again. So this is divided here, so almost you will find 6.64 and 10 to power, you see that is 7. If you deduct here 7, so that will be 10 to power minus 27. So minus 27 divided by 5. So after that 5, you will divide 6.64 by 5. So 5 ones are, and that is almost 33 10 to power minus 27. So that you will find that kg meter per second. That is the momentum. Now we are coming to the question number 3. We'll see what question number 3 says. An, an atom absorbs photon of 500 nanometer and emits another photon of 700 nanometer. Find the net energy absorbed by the atom in the process. Okay. So what we'll do, we have another formula of energy, that is 12400 here, lambda in nanometer. Okay, that is the easy formula. Then but this gives the energy in the electron volt. Yes, but we know that 1 electron volt is equal to 1.6 10 to power minus 19 joules. So we'll convert at after calculation in joules. Okay, I think that's easy. So initially the wavelength is given to be, lambda 1 is given to be 500 nanometer and lambda 2 is given to be 700 if I'm sure, yes, nanometer. So you see, if calculate the number of, find the net energy absorbed by the atom in the process. So let us suppose this is coming with E1 at lambda 1 and going at with E2. So you see here the wavelength is less, energy will be more, means whatever the change in energy of photon is absorbed by the atom. So you see here you will write what, 1240, that is 500 minus 1240, that is divided by 700, but that energy will be in electron volt. So to convert in joule, will multiply 1.6 10 to power minus 19, so that will be in joules if you want to calculate in joule. So you see 1240 and divided by 100 you will take. So here you are remaining with 1 by 5 divided by 1 by 7. 1.6 10 to power minus 19 joules. Okay. So here you will find 12.4 and that will be 7 minus 5 is 2 divided by 35. That is 1.6 10 to power minus 19 joules. So here you see that is 12 point, if you see here you will find that is 12, almost double, not at all, but almost double you will find here. Okay, more than double, yes, that is 12.4 and that is 35. So if you multiply this, you will almost find 25 and that is 35. that is UC, and here is 1.6 10 to power minus 19. So you see here you find almost 5 by 7, 1.6 10 to power minus 19. This you will find. If you multiply this, you will find almost 8 divided by 7, 10 to power minus 19. So if you solve this, you will find almost 1.1 10 to power minus 19 joules. So that is the energy absorbed by the photon. That atom, whatever energy is lost by the photon, that is absorbed by the atom. Okay, now we are coming to the question number 4. What does question number 4 says? You see, when calculate the number of photons emitted per second by a 10-watt sodium vapor lamp, assume that 60% of the consumed energy is converted into light, wavelength of light. Okay, you see here is the bulb. You take a bulb here, and whatever energy is given to be the bulb, that is converted into light. Let's suppose its power is 10 watt, but only its efficiency of bulb, basically you can say, of conversion of this energy into the power is 60%, means will take 0.6. And power we know very well, this is given dn upon dt, that is the number of photons falling per unit time, and hc by lambda. So here you will take, so net power which is going to be converted into light. So for that we have to multiply the efficiency also. The 0.6 into 10, that is the energy given, that is the power of bulb, and that is dn upon dt, that we have to calculate the number of photons falling per unit time. And now you see here h we know 6.64 10 to power minus 34. C is 3 into 10 to power 8, that is the speed of light, and lambda is given to be 590, but this is given in nanometers, so we'll write 10 to power minus 9 like this. From here we have to calculate dn upon dt. So dn upon dt could be written as, this is 6 and 590 10 to power minus 9, and divided by 6.64 10 to power minus 34 into 3 into 10 to power 8. So you have to solve this. We'll find the dn upon dt, that is the number of photons falling per unit time. So you see, we'll calculate this. If it is goes in numerator, that will be plus, that is minus sign, that is minus 8, and it will go, that is plus 34. So this solved. So you will get how much? That is 17. So 10 to power 17. So you got 6 into 590, 10 to power 17, and this is divided by 20. This and this multiplied, so it will be almost 20. This cancel, so you will get this. So almost you will get 1.8, because if this is 60, so you will get basically 180. So almost you will get 177, if you see, because 9 3s are 27, and that is 10 to power 17. So if you take this, adjust the decimal, you will find dn upon dt, that is 1.77 10 to power 19 photons per unit time. So thank you. We discussed 4 questions. In the next video, we'll discuss the further questions. Thank you guys.